Okay, good afternoon, YX students. I had to say YX students actually because they're actually my focus now. I haven't gone through rigorous teaching for the UTME students. Now the focus is for those writing the WAEC or NECO respectively. And I told you I will be coming regularly online to teach and mathematics, physics, chemistry, and of course further maths as the case may be. And today or this afternoon, I'll be looking at alternating current circuits. Alternating current circuits. That's what we're looking at this afternoon. Alternating current circuits. Alternating current circuits. So that's the topic this morning or this afternoon rather. So if you are with me, you can share with your friends. Let them follow the class live as I start now. So I will major more on calculation. I'm going to major more on calculation. I'm going to be solving calculation more. I'll just do a little explanation. Remember, WAEC is starting in the next few weeks. And so my focus is questions you are likely to see. So not just telling stories, but solving questions and explaining what is being solved. I think that's the bottom line, okay? So it's more or less like a revision class, okay? So I'm not going to be telling you the nitty-gritty and the intricacy of the topic, okay? I just touch, and then the important things you need to know to be well prepared for this particular topic. Okay, so we look at the word alternating currents. Alternating currents is actually a current that moves or goes in a sinusoidal way, or that moves sinusoidally in such a way that it's like reversing its own direction periodically. Okay, so alternating current is a current. It's a current that varies sinusoidally in such a way that it reverses its direction periodically. So that's what we mean when we say alternating current. And so you have a situation like this. I don't need to tell you a story about Thomas Edison. You don't need all the story. Thomas Edison and Tesla. These are people you attribute your DC and AC to. These two men, Edison and Tesla, actually they were together before they separated. Okay, so you have a situation like this. At this very point here, you know, if I was to teach you we usually call this place what we call maximum displacement, what you call amplitude, or what you call your crest. But here, that's not my focus. So my focus here is not about amplitude or crest. My focus here is V naught. Let me just use here either V naught or I naught. Okay, this one V naught or I naught. You understand what that means? So what does that imply? I just told you that alternating current is a current that varies sinusoidally in such a way that it reverses its direction periodically. You could see what is going on, unlike your direct current. Okay, now there's a general formula I could introduce to you when looking at alternating current. Okay, there's a direct formula, either this or you write it this way. Okay, so both are actually allowed. I'm going to be defining what each of these parameters means, or what they connote, or what it implies. Okay, so you could also write it this way. I naught. You have it this way. Both are actually acceptable. Both are acceptable. So if you look at what I have on the board, you will agree with me that solving a question like this or understanding this equation is very, very pivotal. Okay. Now, looking at this particular, please, I need, okay. Okay, so I'm going to be explaining the parameter. Okay, I will explain the parameter. All right. So looking at the parameter, my V is my instantaneous voltage. What do we mean by instantaneous voltage? We mean the voltage at that instant of time. In calculus, we have what we call limits at that particular instant of time. Limits at that particular instant of time. So that's what we mean when we say that instantaneous voltage. The voltage at that instant of time. And then we have this one, V naught. Our V naught means our peak or our maximum voltage. Our peak or maximum voltage. That's V naught. That's what we mean by V naught. Okay. Now what's this? This is called angular velocity. Actually, it's not wrong if you call it angular frequency. Maybe you don't know that. Okay, but you can know it today. It's also allowed. Angular frequency, that's permitted, that's allowed. Okay, angular velocity, or you call angular, what do we have again? Okay, you have T right there. Okay, you have T right there. So, our FT together is called our phase angle. It's called the phase angle. When you combine the two together, and do not forget that your angular frequency or your angular velocity has a formula, and that's 2 pi f. See, 2 pi f, sorry. Okay, so you have that as your angular. That was why when you look at this, V is equals to V naught sine WT omega t. You could see that in place of angular frequency or angular velocity, we substituted 2 pi f for it. Okay, I'm sure that's very clear. That's clear to you. Okay, so one other thing do you need to know here is quite straightforward. Please endeavor to follow the class and make sure you ask questions where necessary. Ask questions where necessary. Where you're not clear, drop question in the comment section and then it will be attended to by Tutor Yomi. Okay, so now what's the next thing we need to do now? I haven't shown you the way the AC equation or AC circuit general equation. The next thing you want to know is what we call Samuel Johnson. Okay, so now send to API platform. So now the next thing you want to look at now is the voltage root mean square and the current root mean square. The voltage root mean square and the current root mean square. Okay, so how do I explain this? What do you understand by this now? Now, I hope you know that when explaining voltage and current in your DC, that's your direct current, is quite straightforward. But when you're doing that in AC circuits, it has some complexity, some level of sophistication, okay? And because this thing is actually measured in root mean, okay? The voltage is measured in root mean, and what happened at your voltage root mean square? What happened? What happened at your current root mean square? Okay, is important you know that. Now your phase angle actually is important, so I don't want to go into too many talk. Just know that our phase angle at voltage root mean square, our phase angle must be angle 45. So in case you are asked that at voltage root mean square, the phase angle is dash A 45, B 30, C 60, D 90. You know that the answer is 45 degree. Okay, so the phase angle at voltage root mean square is what? It's 45. And let's see if it's actually true. Let's see. So we have V naught, we have this 45 degree. Okay, good. Now compare it with this so that you're not wondering what's Tutoyomi doing. So you could see that in the place of the WT, the sine 45 degree has occupied it. Okay, so we can do something quickly. So we have this. What's your sine 45 degree? That's root 2 over what now? Over 2. Yeah. Root 2 over 2. Yeah. Root 2 over 2. Or we could say that sine 45 degree is something like this too. Is allowed? Okay. So can I say that if you have something like this, can I say then that my instantaneous voltage and my root mean square voltage, now maybe I should do it this way. I shouldn't do it this way. Some students may be wondering, Mr. Ami, what did you do? Okay, I like you to know that what I did now is the same thing as this. Yes, so this is voltage over this, or 0.771 V naught is allowed. This is also allowed or permitted. What I simply did here was I rationalized, okay, with the denominator. I just rationalized, so that's what gave me this. So do not be confused. If you know yourself very well, that won't be an issue for you to comprehend. I'm sure that's very clear. That's very straightforward as well. So let's go straight to the next thing. You can see clearly here that our voltage, instantaneous voltage, is equals to the peak voltage, and then we have this, and you can see. So it means that at your voltage root mean square value, your sine 45 degree is what you have, and that's how you got that. We got that relationship that we have above. We can also do same for our coin. How? Our coin therefore will be this over this, or 0.71 I coins. Please, I'll need calculator later. Okay, don't worry, maybe.
This calculator.
Let me download calculator. Is there already? Oh, beautiful. Okay, so I think this is so clear. So the next thing I just want to look at is, before we go, I want to solve questions. So question number 1. Excuse me, please. Question number 1. So what I've defined, or what I've derived so far, can we do some calculation on it? Yes, we can. We can do some calculation on what I've done for now. And so that's what I want to do I want to quickly solve a question. Please, let me get question from here. Okay, so question, a quick one. Please hold on. I want to get question from question 1. I have a question here. Okay. Question. I'm here to say question now. Oh no. Okay, I think I've seen question. Yes, I've seen question. Question number 1. It says that the instantaneous voltage of an AC power supply. Ma. Well, I'm teaching. The instantaneous voltage of an AC power supply is given as this. Calculate the value so want to calculate the number 1 peak voltage. 2 root mean voltage. 3 angular frequency. I told you angular frequency is the same thing as angular velocity. And then number 4, frequency of the instrument. So these are 4 questions from the given equation. Okay? So we are given this, and then we're going to do justice to it very quickly. If you're writing, you want to write fast. If you're following, you want to follow fast as well. So looking at the question above, I want to believe the questions. This question in particular should be familiar to you. It's not a difficult question. The question is quite straightforward. And if you were following as I was deriving the formula a while ago, you should be able to solve this. And so we will do it together now. I will explain. And I don't think there will be issue at all after the explanation. Oh no, my board is looking. It's all right. Okay, so we have this. We have the instantaneous voltage. So let's be fast about it. Solution. The instantaneous voltage of an AC power supply is given as V. Our instantaneous voltage is given V. So we're told to calculate number 1, the peak voltage. Of course, the first thing I like to do is to even write the general formula I gave you earlier. Okay, these are general formula. You could also change this to something else. You could change it to V naught sine 2 pi what? ft. I said that if you were following from the beginning, okay? So now, we are told to do what? What are we told to do? See what we are given. So it's very easy for us to do justice to it. This is not a question we need to rack our brain on. Okay, so look at it now. Doing what we call juxtaposition. Okay, comparing and contrasting. Okay, so you will agree that our peak voltage is 100. So, over figure 1, our peak voltage V0, which is number 1 now, is 100. That is, look at it right here. Okay, I'm sure that's clear. Number 2. Number 2, the root mean voltage. That's also straightforward. We say that that gives you what? This. And then we said that that can also mean multiplying this by 7071. Okay, so we already know our peak, right? What's our peak? Look at it here. And so we have 100 multiplied by 7071. And that's 100, that's 70 plus what? 71 voltage. Okay, you can multiply. And with calculator here, so in case you are in doubt, I'll also punch my calculator. So that's what I have, 70.71 voltage. So that's number 2. Number 3, they said angular frequency. Wow. Okay, angular frequency. What should that be? Okay, so can we can we make our comparison again? What's our angular frequency here? Please cause answer, students. If you're following, please drop it in the comment section and tell me. Look at it now. Okay, this for this, this for this, and what we follow. Look at it. Make comparison. Exactly. So my angular frequency or angular velocity is 20 per rad. 20 rad what? Per second. 20 pi rad per second. Okay? 20 pi rad per second. That's the answer. So that's it right here. You can see it now. Compare. I just told you to compare now. And then the fourth question, it says that we should find the frequency of the instrument. Okay? I think this one is quite straightforward. So we just remember our formula. We know that frequency is this over 2 pi. And if this is 20 pi, and this is 2 pi, pi we cancel pi, 2 here 1, 2 here 10. Therefore, our frequency is 10 Hz or S. So our frequency is 10 Hz. Is there any ambiguity in what I've done? That is there anything you probably did not get? Was there something I said now that was a little bit difficult for you? Edosa, John, you're watching? Okay, do you have question? Please. Is everything clear to you? Is everything clear? Okay, is everything clear to you? I want to believe it is clear. And those who will be watching later, I want to also believe that it's going to be clear to them. Okay, so I want to move to the next thing very carefully now. And the second thing we'll be looking at now has to do with solving question, understanding our capacity reactance and all those stuff. Because I am actually interested in calculation. I'm interested in calculation. So I like to wipe the board. Okay, I like to wipe the board now. But I want to make the board clean. It's looking a little bit, so let me get something and wipe the board. Okay, so I'm using this to wipe the board so the board can the board is dirty, so I'm trying to use so we move to the next thing. So the next thing we want to look at, I still like to clean the board better than what it is. So I like to clean the board better. So before I clean it better, let me explain the next thing we're going into. The next thing I'm going into has to do with explaining capacity reactance, inductive reactance, and relating it from our knowledge of Ohm's law, or relating it with our knowledge of Ohm's law. All right, relating it with our knowledge of Ohm's law, then bringing it into other, how it relates with inductance, capacitance, and then resistance. Okay, now you must know this, that what resistance is to a DC current is what impedance, okay, capacity reactance, inductive reactance is to an AC current circuit. Okay, what resistance is, because all of these, they oppose the flow of currents. All of these, they oppose the flow of currents. Okay, all of the things I've said now, they oppose the flow of current. So I'm just trying to wait so I could clean the board better. That's why I'm not writing on that board. The board is looking thank you. So I want to go. This is better. I guess it's the marker that is. So maybe I will use a particular marker. This marker I'm using is the one causing. So this marker is the one causing this. So I think that's the issue now. So, and it's taking my time, which I don't like. It's taking my time. Okay. So it's taking my time. I want to make sure that the board is properly white. So I need something to dry it up now, so I can start serious solving. It's very unfortunate that I did not envisage this. So okay, I think I might need to manage this, but it's still not dry. So I want to get something to dry it up, and then when it's dried up, I would like to use another marker entirely. I guess it's the marker I'm using that is actually making it this way. Thank you very much. So let me just, okay. The essence of all this, so that my student can see what I'm doing clearly, nothing more. So I'll find exactly why it is like this. So the whole essence is so that those of you watching, you can have a clearer view of what I'm doing. Okay, so let's go. So now the next thing is, I want to look at, because I want to solve question, what I want to call resistance, and reactance. Okay, so these two actually are opposition to the flow of current. These two, both reactance and resistance. This is basically for your DC, and why this is for your AC. But they have something in common. We can relate them. I told you I'm not interested in too much story, so I want to go straight to the point. They both what do you call it now? Resistance opposes the flow of current, DC current to be precise, and this is AC current. So we have what we call capacitive reactance, and we have what we call inductive reactance. Okay? Now, look up. So, considering inductive reactance, please just, these are things you should know, not story. Okay, so it is represented with XL, and this XL is, we have it to be 2 pi L. In other words, it can also be L, and then you have WL. Now, this inductive reactance, okay, it's important. This is your, this one is given in Henry, that is your inductance or inductor. Okay, this is your frequency, and so when they give you inductor, okay, or your inductance, the question will just come. They could say, oh, where the inductor is 2 milli. Okay, I'll continue from here. I've actually explained the reactance, the resistance. I've explained it. You know, there are issues with online teaching. Sometimes I was doing that. I'd explained it. I'd even derived formulas. The formula rather, I was about solving question when network issue came up again, and so we had to delete. That has to be deleted again. So I'm continuing from where I stopped from the first video. Okay, so I'm going to explain this over again. I've done that before now, but since the video is deleted already, you may not have captured what I said in that video. Resistance and reactance. Okay, resistance is opposition to the flow of current. Actually, DC current, DC, and then reactance is also opposition to the flow of current, but this time AC. Okay, so this is DC and this is AC. Both oppose the what? The flow of current. Okay, now the reactance is actually divided into basically two. We have the inductive reactance, the inductive. So inductive reactance, we use this. So inductive reactance using this. So this is XL. My XL here is the inductive reactance. It gives me angular velocity or angular frequency multiplied by L. L is given in Henry. That's the unit of L. So we have what we call inductance. Like you have your capacitor and your capacitance. Okay, so it's given in Henry. Now, you know that this is also the same as our 2 pi d. Therefore, our XL is now given as, instead of this, replacing it with 2 pi, So we have 2 pi FL. This is it now for our capacitive reactant. And of course, I'm going to relate it with Ohm's law. I've even written it. I told you I've done the video before, so I'm just writing again. Now, for your capacitive reactance, I wouldn't want to wipe the board. I don't want to wipe the board again, so please kindly bear with me. Still on the AC circuits that we're doing. So I'm done with inductive react. Actually, I'm having network challenge. That's why all these break that I'm having. There's a kind of network challenge. My mind is made up to actually touch it to a point before I will stop today. If not, I would have probably given up because of some of the things I'm experiencing. Okay, so inductive reactant, this is quite self-explanatory, and I've already done justice to it in the last video. So you have this is your angular frequency or angular velocity, and then you have your inductor here, and then you have your frequency here, because in place of this, you could have this, and then you have this. So for capacity reactance, you have your Xc equals to 1 over 2 pi c, your Sc, or we could say that this. Yes, so this is what you have for your capacitive reactance. Do not forget, from our Ohm's law, our V is IR, and so relating it now, your voltage root mean square is equals to your current root mean square multiplied by your inductive reactance. Okay, so you have it. Just compare and contrast. The same using the peak current and the peak voltage. You have the same thing here. Remember that this and this are both in ohms, including this. They are in ohms. So do not be thinking what will be the units. The units is actually ohms. So that shouldn't be a problem. So they are all opposition to the flow of current. Okay, all of these that you're seeing on the board. So this is square. Now let's solve this question carefully. If the frequency of the EMF, the electromotive source in the circuit, is 500 over pi s, what is the reactance of the inductor or 2H? Okay, so what we mean here is that they are asking us to find our XL. XL is what we are looking for. XL is what we are looking for. And to find our XL, so we use our formula. And so we have two. Okay, I like to draw a diagram for it. I think it's good we draw diagram. Yeah, it's good we draw diagram for it. To get your full mark, draw a diagram for a question like this. So they gave us 2 ohms. Okay, so this one is a 500H, what's that, X over pi, yes. Okay, so you have that now, thank you. So this is the diagram for it. You could just sketch something out like this. So from here, we are told to find the inductive reactance, which is 2 pi L. So we have 2 times pi. Our frequency, okay, is given, yes, 500 over pi. And then inductor is given. Okay, so we have pi cancel pi. So 2 times 500 times 2. I think that's 2000 ohms. That's 2000 ohms. The question here is quite straightforward. It's quite straightforward. So we're not going to waste time on that. So I'd like to solve one more question. Let me look for a question to solve. Time is going now. So I want to solve a more critical question. Okay, even this question I want to solve now is not even as it's not really critical. It's just almost similar thing. And then we're going to solve some question later. Okay, so the questions number 2 or maybe number 3 says a capacitor of capacitance 25 millifarad is connected to an AC what? AC power source of frequency calculates the reactance of the capacitor. So this one now, if you look at the question is very clear. We are told to find what are we looking for? Let me go back to the question. Find the reactance. It says a capacitor or capacitant. So we are given our capacitance. We are given, what are we given again? We are given, let me look at the question properly. Are we given frequency? Yes, we are given our frequency. Yes, 200, exactly. We are given our frequency, 200 Hz. Okay. So what's the next thing? We have to look for this. So this is quite straightforward. And it's just for us to employ our formula. It's there on the board. I have not wiped the question. The formula is still there. So we could also draw, or let's sketch something for this. What's that now? Okay, 25 each. Okay, so we could just sketch something like this for it. So the question says that we should find, what are we looking for, please? We are looking for SC, which is this, which is 2 pi FC, which is 1 over 2 times 3.41 times 200 times, what's the capacitance? Okay, capacitance is given in millifarad. Okay, farad, that's, is going to be 25 times 25 times 10 raised to the power minus 6. Oh, that's serious. That's serious. So if I'm to write that correctly, I'm going to have XL is equals to 1 over 2 times 3.14, maybe 2, times 200, the frequency. So you have this. So if you multiply that correctly, you can do that at your end. Multiply correctly. you're going to have 0.318. 0.31818. 0.31818 ohms. So if you are to take it to 3 decimal places or 3 decimal place, you have 0.318, okay? Or 4 is 0.3182. So that's for that. So that takes us to the last thing I would like to consider: impedance and resonant frequency. Now, impedance, like, how do you explain impedance? Well, I'm not going to explain too much. I'm not going to be talking and talking and talking. Okay, so impedance here, I would just want you to know that impedance here incorporates your capacitive reactance and also your inductive reactance. So, how do we explain impedance? We say that the impedance has to do with the overall opposition that is being offered to the passage of an AC that is being mixed, an AC mixed circuit. Okay, so it's just an overall opposition. It incorporates the inductive reactance, capacitive reactance, and also you have what we call the resistance itself. So bringing all of this together, that's how you have your impedance. Okay, that's how you have your impedance. And basically you must note that our impedance also is is actually opposition to the flow of AC circuits. Okay, is opposition to the flow of AC circuits. So you have something like this. This is your impedance. So where your X equals to your XL minus your XC. So if I am to doing that correctly, so we can say that our Z impedance is equals to R square log XC this all square. Okay, so this is something you need to commit to your memory, and this is something you need to recall when question is being asked. You need to recall this, that whenever you are given question, recall that that is very very important. And if you remember, I did say that from Ohm's law you have your Ohm's mean, square currents, and all of that. So it means that if we are to employ what I said then, remember I said from Ohm's law you could have, can you remember? I said you could have this XL. You could also have it as SC equals to VR. So will it be wrong for me to now say that? It's alright. So I still want to continue from where the last video stopped. Okay, I was actually deriving something and didn't know that my video has stopped. Okay, so I will continue from there. I never planned that I'll be repeating myself over and over like this. I guess I will work on that later, network and data issue and all that. Now, okay, so I was trying to say something. The impedance and resonant frequency, we had established what impedance is in the last video. So coming to something here now, I also say that we could have it this way. Okay, but there's another thing we could also establish. We could also establish that, okay, from our V, which is root mean square, root means square, multiplied by SC, or our VA, root means square, multiplied by XL. Okay, since we have impedance, it will not be wrong for us to write something like this, multiply by impedance. Remember I said that impedance incorporates the resistance, capacity, reactance, and inductive reactance. Okay, it incorporates all. Okay, so the overall opposition to the flow. Okay, so you have this now. Okay, now we could also write another thing that look like this. So let's see if it's also acceptable. You could have something like this, square, okay, and egg this. You could have this is allowed, square it, and then you solve. This is actually gotten from the knowledge, Ohm's law, triangle this, Pythagoras theorem. Okay, and I remember very well that in terms of our power factor, now before I derive anything here on power factor, I want you to remember that your work done, I'm not talking of work done of first time resistance, not this. I'm talking of your work done in an electrical circuit, which is your quantity multiplying by voltage. That's the work done in an electrical circuit. And then we have this one, that quantity times time times voltage. So we could say that IVT is your work done, right? Yes, IVT is your work done. And if that's your work done, let me wipe this part of the board. If IVT is your work done, okay, so I have IVT. I know that my power is work done over time, which is IVT over T. Cancel, cancel. Power is IV. So you have this as your power. And of course, from Ohm's law, I know that this is this. And if I make, if I make this subject of formula, I could have, look at it now. If I make it subject of formula, I could have my W to be I squared T. So therefore, my power is R squared T over T. Cancel, cancel. So my power is I squared R. So my power factor here can be this, cos theta. I could also write it as R squared what? Cos theta. So if the angle is not stated or clearly written out or given, you could use it to be power equals to IV. Actually, all of this came from here. And that understanding should be imbibed or should be taken note of. I'm sure that is very, very clear. As I want to solve, wrap everything up, I'd like to show the last part of this work. And that's the part of resonance frequency, okay? At resonance frequency, you know that your impedance is minimum, and what happened again? Your XL is equals to your XC at resonant frequency. Your XL is equals to your what? Your XC. So you have what now? What do you have? You have this XL. XL is 2 pi what? L. And this one is what? 1 over 2 pi, 2 FC. So we're talking of what happened at resonant frequency. I was talking of your impedance being minimum. And also said that what happened is that your inductive reactance and your capacity reactance become equal. And we could do something about it here. Let me see if I could just do something. Let's cross multiply. So you have 2 pi FL multiplied by 2 pi F what? C equals to L. So I have my square. Yes, I have 2 times 2, 4. I have pi times pi, pi square. What again do I have? Then I have my c equals to 1. So if I have this, and then I'm going to have 1 over 4 pi square c. Is this understood? I think there's another thing I didn't write, L. Okay, there's L, sorry. There's L, yes, L. Okay, so I could write it neatly like 4 over pi square LC. Okay, so for me to remove the square, what do? I can square both sides. I have 1 over 4 pi square LC. So F therefore is 1, you have 2 pi outside over what? Your LC. So the square root of 4 is 2. And then this one you have it here. This one you have it here. Square root of 1 is 1. So this is very clear. So this is called resonant frequency. So that's our resonant frequency. So do not forget your impedance is minimum, and at resonant frequency do not also forget that your inductive reactance is equal to your capacitive reactance. Your inductive reactance is also equal to your capacitive reactance, and that's how that is gotten. I think I would like to solve the last question. The last question I want to solve, and I will stop here. Yeah, students, I'm going to stop here. Let me just put questions on the board, or maybe I'll put a question and then you can do justice to it, or I will explain it myself. Okay. So here's the question, a very standard question at that. So this question incorporates resistance and it incorporates resistance. So here you have 100 ohms. Here you have 10. The other question is also, this is microfarad, that's raised to power minus 6. And then here you have 90 volts and 25 hertz. So voltage and frequency are given here. And then the question says you should find, we are told to find, calculate, the average power used in the circuit the phase angle A and 7 the power factor. Okay, so this kind of question is quite extensive. If you have been following very well, you will see that the question I just gave now is quite extensive. Question number 1. Let's read the question. The question is on the board already. Calculate the following in the series circuit above. 1. Reactance of the capacitor. Okay, so that's the inductive reactance. Okay, that one is quite straightforward. The number 2, they said impedance in the circuit. Number 3, current. Okay, we are looking for the current. Okay, so we are going to release something as well. Number 4, they said we should find what now? Voltage across the capacitor. Okay, so we are looking for the voltage the voltage across the capacitor. So it is assumed that we have known the capacity reactance, and then if we have known it and we have known our current, we can easily find the voltage across the capacitor. So that's not an issue at all. And then number 5, we are told to find the average power. So I might not solve everything for you. You might have to do some of them yourself. I've given you the formula, but I will just explain them, and then maybe you can tell me the answer. I didn't know I would stay too long like this in the teaching. So let's start. Let's just do some of them quickly. So we have reactance of the capacitor. Okay, I think that's talking about XC. That's 1 over 2 pi FC. Okay, so I think this one is just straightforward. 3.42 times, what's frequency? Is it giving? Okay, yeah, it's giving 25. And then the capacitance is given as our microfarad. So it's going to be 10 times 10 raised to the power minus 6 because it's in micro. Please take note of it. If it's in millifarad, it will be minus 3. But if it's in microfarad, it's going to be minus 6. So you could solve that now. Please, if you are following, let's just get a calculator and put the answer there. Okay, I need the answer for this. Okay, so multiply very well. You are going to have that 6.3 and 62 ohms as you multiply it. Okay, so multiply that correctly. Number 2, the impedance in the circuit. The impedance. Okay, number 2, impedance has to do with what now? So the impedance, okay, so let's look at this now. So that's it. So just let's punch calculator for this. This one requires serious punching. If you are following, please make sure you follow well. So let's punch calculator. Remember, we have our XL here is 0, and so we are using this. So let's punch calculator 100 square. And then what do we have here? Let's put it here, 662. Okay, please kindly confirm for me, those of you that are watching online, so you can confirm for me, Emmanuel, and others who are watching, please confirm for me, when you multiply this, what's going to give you? Confirm. What we have here is, as you do, is 64443 ohms. Okay, so that's the impedance. Remember, our X inductive reactance is 0. So that's why we have it this way. Do not forget that. Number 3, we are told to find the current through the circuit. Okay, I think that's straightforward. I told you that number 3, that's this like this now. This is allowed. I explained to you. So we already know this. We know this. So this is 90. Where is it? Okay, it's given. Look at it in the circuit. And then I is what we are looking for. Z is known. 64443. So making I subject of formula, divide it. All these things are so simple, eh? Please, let's punch calculator again. 90 divided by, so you have 0.14 ampere. Okay, so that's for that. Now, you help me do the rest. Let me just tell you what to do. I want to stop here. Number 4, what do you do? Voltage across the capacitor. What do you do? Okay, let me explain what you will do. The voltage across the capacitor, for us, we have known this. We have known the current. So we just recall and say this, XC. That's the formula for Roman figure 4. So you can do that yourself. So you are multiplying currents that you have known. What's current? Where is it? I thought we saw for current. Yes, see current here. Multiply it by what? Where is it? Where is the ahead? Then you get the voltage across. So the average power used in the circuit, 5, we have something like this. We know our resistance, right? And then we know our resistance, and then we know our current. Oh, that one is straightforward. And then our phase angle. Oh, you remember what I call phase angle? I hope you still remember our phase angle. What's the phase angle again? What did I say about it? I need an answer from you. Drop it in the comment section. The power factor, I derived the formula for you. I need an answer as well. So give me answer to number 1, the power factor, the phase angle. I need it on the, drop it in the comment section. Just tell me your answer, and then I will know if you are correct or not. So this brings my physics class to an end this very morning, this very afternoon rather. For those in the university, I'll be coming up in the night to teach. I'm likely to let you know the time. I might be teaching what we call differential equation. That is not for secondary school students, except if it will not purge your tummy, you can join. Well, if you are going to be studying engineering university, you can join the class in the night. I'll be having that class after my program in the church. So you can wait for me in the night. I'll be teaching differential equation. Till I come your way again, I remain my humble self, Yomi Omorewa. Bye.